Hello guys, we're going to have a look at strictly increasing and strictly decreasing functions. Now, it is a little bit of a dry topic, but look, don't worry, we'll sort it out and I'll give you all the tools you need to get all the questions you might get in that area right. Now, it can be a bit confusing just by eyeballing functions as to whether at first glance they're strictly increasing, for example, or for that matter strictly decreasing. For example, this function here is always increasing with increasing x, isn't it? And it also is strictly increasing. This function here is not always increasing. Well, it doesn't look like it is. It's got a flat bit in the middle, doesn't it? But according to the definition of strictly increasing, it is strictly increasing. Now I've got you confused, haven't I? So come on over the screen and we'll sort it out. Okay, here's the definition. We need the definition before we can do anything, okay? So a function is said to be strictly increasing when for a is less than b, they are x values, less than b. This implies that the y value, f of a, is going to be less than the y value, f of b, for all a and b in its domain, or within that interval, okay? So that makes a bit of sense, doesn't it? Kind of makes sense. If this is to the left of this on the x-axis, for example, then this value has to be less than that value if it's going up. Well, that makes sense, doesn't it? I think it does. So this definition does not require f to be differentiable. So it can have a kink or a cusp in it, or to have a non-zero derivative. Now that's interesting. In other words, you can have zero derivative. Now that's a bit crazy, isn't it? For elements, all elements in the domain. So I'll just read that again. This definition of strictly increasing, this is where it's strictly increasing, the definition. It doesn't just necessarily mean increasing, it's strictly increasing by definition. So this definition does not require f to be differentiable. Well, that makes sense, kind of. Or to have a non-zero derivative. So it can have a zero derivative. That bit's confusing to me, for all elements in the domain. If a function is strictly increasing, then it is a one-to-one function. Okay, I'll buy that. It has an inverse function which is also strictly increasing. Well, I'd have to look at a graph to work that out. That's probably right. Now, yes, does not have to be differentiable. Well, we got that. But this bit here does, or to have a non-zero derivative. Okay, that's pretty interesting. And if it's a strictly increasing function, then it is a one-to-one, blah, 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 has an inverse which is also strictly increasing, would be one-to-one as well. Now, have a look at this. We've got here, so we've got a function such that real x's map to their real corresponding y values, where f of x equals x cubed. That is strictly increasing, as I was saying on the first screen, with zero gradient at the origin, as illustrated in figure 1. Well, there's figure 1. Now, what about the stationary point? What about that stationary point? This is the point where we have a zero gradient, right? So if y equals x cubed, we know that dy dx equals 3x squared, okay? That's fair enough. Now, if dy dx equals 0, then 3x squared equals 0, which means that x must be 0, okay? Now, this is the $64 million point that I want to make in regard to strictly increasing. This means, guys, that x is 0 is the only point, one single numero uno point at which the gradient equals 0, right? It's not really flat in that sense. It looks flat for a while there, but really it's not. It's always going up and has a 0 gradient momentarily at one single infinitesimal point where x equals 0, then it's going up again, right? Now, having said that, so by the definition of strictly increasing, okay, if you have if x is less than 0, then immediately to the left of that point where x is 0, the function will have a lower value, a lower y value, a lesser y value than at 0 itself. The value of the function at 0 in this case is 0. So immediately to the left of 0, the function will be less. In fact, it'll be negative. It'll be a negative value, okay? So, see, that fits our definition of strictly increasing, providing that it only has a zero gradient at one single point and then continues to go up after that as you go, x goes to the right, yeah? Yeah, and as I was saying, okay, f of, what's that saying? Oh, yes, okay, so as you go to the right of where x is 0, the function is more than its value at x is 0. So, all right, so can you understand what I'm trying to say there? So what I'm saying is that for every point along this trajectory, for every value of x, immediately to the left of whatever value of x you pick, including where x is 0, the value of y is going to be less than the value of where you are at any point. Okay, if you're to the left, the value of y will be less than the point that you're considering. All right, so just to hammer the point home, well, let's say x is 0. Okay, if x was minus 0.10 zeros and then a 1, f of x will be less than when the value of f of x when x is 0. Yes, and if x was 0.10 zeros plus with a plus and then a 1, the value of f of x will be more than the value of f of x when x is 0. You see, so it does comply. It does comply with the definition of strictly increasing. Okay? Yes, I know. Don't say it. So therefore, f of x is x cubed is strictly increasing for all real x numbers, according to this definition, right? According to the definition. Okay, now what's it say down here? The inverse function, yes, the inverse function such that all real x values map to their corresponding y values where f of x is x to the third. Yeah, that's the inverse. That's also strictly increasing. Aha. That's interesting. If you drew that out on a graph, you would see that. You'd see that to be the case. With a vertical tangent of undefined gradient at the origin, yes. If you just follow my pen, my thingo on the page, x to the third goes like this. Starting there, it goes zzz, vertical there at x is 0, and then goes zzz, like that. And it is the inverse of this beastie here. And yes, so it is. I can concede that and agree with it. It is also strictly increasing. Pretty interesting, huh? Yes. All right. Now we've sort of got over the hump of why x cubed is strictly increasing, and you can sort of get the idea of how this all works now. All right. So what's this? A hybrid function with domain from 0 to infinity, and this rule here, x squared, where x is greater than or equal to 0, less than or equal to 2, and it's equal to 2x for x is greater than 2. What does it look like? Ye gads, look at that. What a stupid looking function. Well, here it is. It's got a kink, right? It's continuous, but it's got a kink here. But the point is, ladies and gentlemen, it's always going up, and it does comply with our definition of strictly increasing. Yeah, it is, isn't it? You can see that. Strictly increasing even though it's not differentiable, yes? Because it doesn't flatten off anywhere at all to zero gradient. Now what's this strange looking creature? A function is said to be strictly increasing over an interval where we've got a is less than b implies that f of a is less than f of b. That's strictly increasing, yeah? For all a and b in the interval. I've just restated the definition of strictly increasing. Thus, this function here, which is a very strange looking animal, we've got mod x minus x cubed, is not strictly increasing. Well, of course it's not. We can see that as illustrated in figure 3. But for a part of its domain it is, though. See, it's going down here, so that's not strictly increasing. But it is going up from this pointy cusp bit here. It's going up until it flattens off at zero gradient, which I think I worked out is the point 1 over where x is 1 over root 3. I think that's right. So yes, it would be strictly increasing for x going from 0 inclusive up to and including the zero gradient local max point where x is 1 over root 3. And then of course it's going down for the rest of its travel. Would you agree? Yeah, now it's very important with all this strictly increasing, decreasing stuff, you get the end points right. That's the bit that they really hammer you on, okay? The pedantic bit. So what have I said there? If the function is strictly increasing, then f of x, f dashed of x. Wait a minute. Abracadabra, I fixed it. That's right, isn't it? Yeah? So where x is greater than or equal to 0, I'm saying here, mod x equals x, and this function, this h of x, which is what they call the function, would be equal to x minus x cubed. Now, I think I'm solving it here for the stationary point. H dashed of x would be 1 minus 3x squared, if you refer to this up here, just taking the derivative. That's right, isn't it? So therefore, the local max occurs when, yes, where this h dashed of x equals 0, therefore 3x squared equals 1, and yes, I had it right, therefore x would be, in this case it would be plus 1 over root 3, okay? Yes, we're not going to consider the negative case because it's a different function over there. Well, it's not x minus x cubed over the left-hand side of the y-axis, so we're only referring to the positive bit over here, right? Yeah, now, where was I? So this, hence, h of x is strictly increasing for x going from 0 and including 0, even though the gradient's not defined at 0, that doesn't matter. X is 0 on the kinky bit, the cuspy bit, and for every point beyond 0 to the right, f of x is greater than the previous point to the left until you get to, and including, x is 1 over root 3, okay? Then from that point onwards, f of x gets less every time you move to the right of any point. You get it? I hope you're getting it. It's a bit crazy, isn't it? All this palaver over increasing and decreasing. That's my CAS handheld version of it. There it is. Now, what have I said there? Yeah, this black curve here is the gradient function of that. It's very interesting, isn't it? See, the gradient is negative, becoming less and less and less and less and less and less negative. The gradient is not defined here. Hence, this black gradient curve is getting less and less and less and less and less and less negative there, not defined there, and then all of a sudden on this side of the y-axis the gradient morphs into positive mode and becomes less positive, less positive, less positive, less positive, less positive, and until you get to the stationary point where the gradient equals 0, and then on the other side of the stationary point the gradient becomes negative. You see that? Now, I think I've got some more stuff in here for you. Yes, this is the open dots here to signify that the gradient's not defined when x equals 0. And from everywhere, the thing is strictly increasing from 0 and including 0, right? Even though the gradient's not defined there, that doesn't matter. Up to and including the stationary point itself, right? So actually, yes, the function is strictly increasing from here to here, inclusive. Yes. And I've just marked in the bit of the gradient graph to signify that. See, the gradient is positive. Gradient is positive, 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 and 0. And that point's included in the strictly increasing, and actually so is this point here, even though the gradient is not defined at that point. Okay, I know. Let's move on. Strictly decreasing. The function f is said to be strictly decreasing. Well, it's exactly analogous to strictly increasing, guys, where a is less than b implies that f of a in this case is more than f of b because it's going down as you move from left to right across the page. For all a and b in its domain, function is said to be strictly decreasing over an interval a to b implies, yes, f of a is greater than f of b for all a and b in that interval. Yes, all right. So what else is new? I'm sorry, my sense of humour is going mad here. This is strictly decreasing. Heavens, it is, isn't it? It's decreasing right along that domain. It is, yes. Very good. What about this beastly looking thing? It's a cos graph, isn't it? Yes, g of x equals cos x. All right, that's all right. Now, we're going to work out, it's not, well, obviously it's not strictly decreasing. We can see that. We're not completely stupid, but we're going to have a look here now. Okay, so where is it strictly increasing? Where is it strictly decreasing, guys? Let's see. Okay, these are I've just marked in the stationary points for you. There it is. Da, 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 da. And I didn't bother to move to do these ones. I'm just doing it from here to here to here, right? Now, all right, can you work it out? Where is it strictly increasing and where is it strictly decreasing? I've marked one complete cycle, all right? Yes, there it's strictly increasing, including the stationary points. That's what I want you to get clear, because that definition of strictly increasing works if you start here and if you finish here. Yes? Yes. Every value of f of b is greater than the value of f of a, where a is less than b, right throughout that interval, including the endpoints. This bit here, that's strictly decreasing, isn't it? Including the endpoints for the same reasons, yes? Okay, strictly increasing, da-da-da-da, strictly decreasing, da-da-da-da, from minus pi to naught, strictly increasing, from naught to pi, strictly decreasing. So you can see that naught, that's the crazy part. The naught gets counted in each. So that, yeah, the 0, x is 0, is the right-hand side of the strictly increasing interval, and it's the left-hand side of the strictly decreasing interval, and it's included in both. Now, I know, but that's it works with the definition of strictly increasing and decreasing. All right. Now, the last bit here: if a function with rule y equals f of x is strictly increasing over an interval, then the function with rule y equals minus f of x will be strictly decreasing. That makes sense, because you're just reflecting it about the x-axis, right? So if it was going up, then once you reflect it about the x-axis, the version that's reflected will be going down. Yes? That makes sense to me, doesn't it? And to you too? Yes, very good. Now here's a summary for us to try and get all this stuff into our heads. If a function f of x is strictly increasing over an interval, x goes from a to b, that is, a is less than b, of course, that's what that means. And, what am I saying? Then f of a has to be less than f of b over that entire interval, which may include stationary points at either end, okay? If a function f of x is strictly decreasing, on the other hand, over the same interval, x is a to b, that is a is less than b, then if it's decreasing, then the left-hand value will be greater than the right-hand value, right? The reverse of what's going on up here. And that's over that entire interval, which may include stationary points at either end. Now, what else have we got here? F of x does not have to be differentiable. No, it doesn't. It can have a kink or a cusp. That's all right. F of x will be a one-to-one function, and its inverse will be 1 to 1. And if f of x is strictly increasing, the inverse will be strictly increasing. And if f of x is strictly decreasing, the inverse will be strictly decreasing. We're going to have nightmares about this. If f of x is strictly increasing over an interval, oh yes, then that's this bit up here. Then minus f of x will be strictly decreasing over the same interval, and vice versa. All right. Now let's do some examples here. Let's do some examples. All right, what do we got here? This is the definition of strictly increasing. This is the definition of strictly... Oh, that's decreasing, that's increasing. So here we go. 28. Show that this function here, x cubed, is a strictly increasing function for r, all real numbers, by showing that the gradient is greater than 0 for non-zero or non-zero x, and showing that if b is greater than naught, then the value of y for that value of b will be more than the value of naught. And if naught is more than b, what's that mean? That means b is to the left of naught. Then f of naught will be greater than any value to the left. Yeah, that's all right. I think I can get that. That's b is one. Yeah, that's right. Yes, yeah, that's for negative b's. Yeah, that means negative b, right? I wish they'd say that, don't you? So, all right. Now, what have we also got to show here? That the function is minus x cubed. All right, is strictly strictly decreasing. Heavens, what did I say increasing for? Strictly decreasing function for all real numbers. All right, look, this is easy stuff, guys. Now we know what all this increasing and decreasing stuff means. The way I would do this, part A, show that it's a strictly increasing function for r. Right, I'll do it, you watch. That means that f dash of x equals 3x squared. Let's draw the graph of that. Now you can see, this is the gradient function. This is the gradient function. It's always positive. The gradient is always positive except when x is 0. And it's only 0 at the point x is 0. One single momentary infinitesimal point where x equals 0. Therefore, it's sticking out a mile that it follows the definition of strictly increasing, doesn't it? So, now, what I've said over here is, if f dashed of x is 3x squared is... Oh, I'm saying now, f dashed of x equals 3x squared is positive, except when x equals 0, as I was explaining over here. So when x is 0, the gradient is 0. That's referring to the graph opposite. Now, here comes the old knockout punch. Here's the actual graph of y equals x cubed. So, what I'm saying is that if f dashed of x is greater than 0 for all x other than 0, then for b is on the right-hand side of 0, fb has to be more than f of 0, and for b on the left-hand side of 0, fb has to be less than f of 0. It has to be. It has to be, as required. That'll do it, guys. That'll do it. Yeah? Now, I've still got to do b, don't I? Alright, let's do b. Come on, Mr. B. We'll knock you off very fast now. F of x equals minus x cubed, therefore f dashed x equals minus 3x squared. There's the graph there. Same reasoning, guys. Exactly the same reasoning. So I'm saying, hence, if f dashed of x is negative for all x except 0, that means that f of x must be decreasing for all x except 0. And if the gradient is 0 at x only, then for any interval x is a to b, f of a must be more than f of b, including where you're talking about that 0 point there, that where the gradient is 0, right? It still works. The definition of strictly decreasing is holding fast, and therefore f of x is strictly decreasing. Okay? Alright, there's 2 more to go. This is 29. Show that, what's this? It looks like, oh yes, y equals x squared. F of x equals x squared. So show from 0 to the right, it's strictly increasing, and show it from minus infinity to 0, that is otherwise on the left-hand side of the y-axis, up to and including 0, it's strictly decreasing. Well, it's pretty obvious when you think about that quadratic, isn't it? But we better do it and show it all properly. F of x equals x squared, f dashed x equals 2x. There's the graph of f of x, okay, x squared, yes? There's the graph of f dashed of x, it's 2x, right? 2x. So there it goes, yes? You right? Now, here's my argument. F dashed x equals 2x, and that equals 0 only when x is 0. Now you can see that. It equals 0 only when x is 0, yes? Now, f dashed x is positive for all x greater than 0. In other words, to the right-hand side of this y-axis here, yes? Hence, for all x greater than or equal to 0, for any interval x going from a to b, where a is less than b or to the left of b, you know that f of b has to be greater than f of a, including at the point where x is 0, because the point immediately to the right of x is 0, the y value is more. So the definition of strictly increasing holds up from 0, including 0, up to and including infinity, which is what they asked us. Boom, boom, we did it, yes? Okay, and the other part is just the same reasoning. Again, f dashed x is 0 only when x itself is 0. F dashed x is negative, see it over here, or it's all negative, right, to the left of the y-axis there, for x is less than 0. Hence, for x is less than or equal to 0 for any interval, again, x going from a to b where a is less than b, f of b has to be less than f of a. And you can see it, look, as you move to the right, f of b is always less than f of a as it's going down. Hence, the thing is strictly decreasing, yes? Good. Now this is the last one. For the function, what is it? Oh, this quadratic-y thing, alright? Then show that the largest interval for which f is strictly increasing is from half, including half, up to infinity. That's strictly increasing, isn't it? Did they say that? Yes, strictly increasing. Right. Okay, I think we need a graph. We always need a graph. So that's what it is. Let's factorise it though first. So I can see the intercepts. The x-intercepts are -3 and +4. Yes, there they are, and here's the graph. Right, that's one intercept there, that's one intercept here. Now, they're asking about the strictly increasing bit. Well, if we do as much of the function as we possibly can to be strictly increasing, what do you think? Yes, I think we have to go from the turning point, right, and then to the right of the turning point, right? Yeah, that's the strictly increasing bit, that from the turning point, including the turning point, and going to anywhere to the right of it. Yes, so we've just about got it solved. The turning point for this quadratic function is at the x... wait a minute. The turning point for this quadratic function is at the x-coordinate halfway between the two x-intercepts, right? So -3 and +4, halfway between them. So that's the average point. So what's... so add them up and divide by 2. So 4 minus 3 is 1. 1 over 2 is a half. So when x is a half, that's the x-coordinate of the turning point. Yes, x is a half. Well, ha-ha! Hello, Mr. Half. Look, we got you, didn't we? So therefore, at this point the gradient is 0, and for all x is greater than half, f dashed of x, that's the derivative of the gradient function, must be greater than 0, and therefore f of x is increasing for all x going from a to b, including the point where x is a half. Yes, from a half upwards. So what did I say there? At all x is less than a half, all x is less than a half, that means over this away, we've got f dashed x is less than 0 and the function is decreasing. I don't mean strictly, I just mean it's decreasing, it's going down, right? This is increasing, not strictly increasing, it just means increasing, going up, yeah? This is decreasing, going down. Hence, the largest x interval for which f of x is strictly increasing, according to that definition that we've been working with, would be where x goes from a half, that would be the minimum value, including a half, and going upwards as far as you like, to infinity, right, as required. We've just proved it, guys, haven't we? We have. I think that's the end. Okay, the end's your friend, and we get the trend, don't we? Alright, I'm going to have a nice cup of tea now, and I hope you are too. So, thank you for listening to all this strictly increasing and strictly decreasing stuff. I hope you get it. If you don't, you better go back and have another look at it. It's really quite simple, it's just a bit dry and a bit boring at times, but hey, it's all part of functions, isn't it? So I'll see you next time. Have a wonderful day, and see you later.